Hey ANPers, this is Dr. Jones checking in. This is ANP1 lecture test for video 9 covering page 10 of the Noteset. The Noteset should look like this, unless you've already read your chapter, in which case it should already be filled in, which would look like this. Okay, so I've got my two Notesets here. All right, so top of page 10, let's talk about the contraction cycle for this video. This is Spotlight figure 1012, page 309. Okay, so this is the part where it says resting sarcomere. So at rest, let's pick a color. Okay, I'm okay with red. At rest, the myosin heads are locked and loaded, so they're energized by the breakdown of ATP to ADP plus PI. So as a quick review, you have an adenosine with a phosphate on it, and the adenosine by itself with one phosphate is an AMP. M means mono for one. When you phosphorylate it, phosphorylation is adding a phosphate group. You make a high energy bond. And now you have two phosphates. So this is now called a DP. D for di for two. And then when you phosphorylate it again, you make an even higher energy bond. And now you have three phosphates. So you have an ATP. So when you use an ATP, you slash that third phosphate off. So you have an ATP, and then you slash that third phosphate off. Chemistry happens. And then you go back to having two phosphates plus a loose phosphate. So that PI, it's a lowercase cursive I. So it's not pi, it's an inorganic phosphate group. There's a difference. So that's what happens. In 2402, we will learn how to build an ATP, and it'll be an ADP and a phosphate and energy. And of course, you release energy with this. So, and there are lots of forms of energy. It's just that this bond right here releases a form of energy that our cells can use. So this breakdown of ATP has already happened at the beginning of our story with the resting sarcomere. These are already ATPs broken down to set to lock and load, like a gun with a cock. It's already been cocked. So it's ready, but the active sites on actin are of course covered by tropomyosin, which is held in place by troponin, and we know the only thing that can make that troponin move is calcium. So bring out the calcium. Number one, so we're at number one now, influx of calcium ions. So this will be where the contraction cycle begins with these calcium. And two, active site exposure, because the calcium bind to troponin, and that pulls the tropomyosin off of the active sites on G-actin. So this is called active site exposure. So now we have ready myosin heads and exposed active sites. So this is number two. Number three, the myosin heads bind. And the binding of the myosin heads is called cross-bridge formation. So that's number three. Myosin heads bind to the active sites. Because again, they were already energized. And then 4 is the power stroke. So if I'm the M line and this is the tail, and here's there we go. Here's the hinge, and here's the myosin heads. The myosin heads attach, and then they bloop, and that's the power stroke. And I'm the M line, so I've got both myosin heads sticking out both sides, attached to 2 different sets of thin filaments. So when my hinges pivot, I'm bringing all those thin filaments closer to the M line. And the thin filaments are attached to the Z lines, so the Z lines get closer together. So it is this myosin head pivoting that is the muscle contraction. This is the part that actually makes the muscle get shorter. Those almost look like stars. Not quite, but almost. Okay, and so in the previous picture, the thin filament ends here at the edge, and now we have pulled because the myosin heads have pivoted. And when they pivot, that power stroke changes the shape of the myosin head, and that kicks off the ADP and the inorganic phosphate, and they go bye-bye. Okay, let's see if I said everything that I've got written down here. The myosin heads pivot on the hinge, pulling the thin filaments toward the end line, shortening the sarcomere. This is the thick-thin filament interaction. This is the myofilament interaction. This is what happens in the zone of overlap, where the thick and thin filaments overlap. This is the muscle contraction. Okay. Number 5, you bind a new ATP to the myosin head, which resets it. So that is cross-bridge detachment. The myosin head lets go, but the myosin head can't let go until an ATP binds to it. So it's stuck until the energy is there to release. And that's what causes rigor mortis, which will we talk about that? Let's see what I have here. No, that's on the next page. Okay. So the reason for rigor mortis is because the myosin heads cannot detach without AMP. So rigor mortis is what happens after death when the body is stiff, and it happens a few hours to half a day depending on like heat, humidity, how quickly the body breaks down. So it happens post-mortem. Post means after, mortem means death, so it happens after death. And it lasts for, again, a few days, several days, depending on temperature and humidity. And what happens is the body, after death, the body stops making new ATP. Eventually, you run out of ATP, and the myosin heads can no longer detach, and that's why the muscles get stiff, stuck wherever they are. Now, eventually, the rigor mortem does end. Rigor mortis, post-mortem, sorry, does end because the Z lines will break down as the body starts to degrade more. So then the rigor mortis is over. So that's why. Okay, so that was number 5. Number 6, the myosin is reactivated when the ATP breaks down into an ADP and a phosphate group and releases energy. It's almost like you've seen this before. And that resets the myosin head so that it's reactivated, ready for the next interaction. So, and this whole thing can happen several times a second. As long as you got ATP, you can keep going. Okay, and now the contracted sarcomere, which I thought I had a picture for. Okay, not. The contracted sarcomere is where I have written down that it happens several times a second as long as there is calcium and ATP. Because if you run out of calcium, the troponin goes back and it pulls the tropomyosin back, covering the active sites on actin, and then there's nothing for the myosin to bind to. So if you run out of calcium, you run out of ATP, you run out of muscle contraction. Okay. All right, so these 5 things here. Number 1, and we're literally just going with what's on the picture here. The first step in muscle contraction, and we've talked about these steps a number of times. Every time the book talks about it, it skips different parts of it. So you need to understand what happens in the muscle contraction. You need to be able to put these steps in order. Okay. So acetylcholine is released. It binds to acetylcholine receptors. That causes a muscle action potential that sweeps down the sarcolemma and down the T tubules. That causes the sarcoplasmic reticulum to release the dogs, calcium, release calcium, which causes active site exposure. How does calcium cause active site exposure? Oh wait, pause, look it up. How does calcium cause active site exposure? That's right. The calcium binds to troponin, which holds the tropomyosin on the active sites on actin. And when the calcium binds to troponin, it changes the shape of the troponin, pulling the tropomyosin off of the active sites on actin. So that's how the sarcoplasmic reticulum releasing the calcium causes active site exposure, which then allows for cross-bridge formation, number 4. And then the contraction begins because what's the contraction? The power stroke. What allows for the power stroke? The hinge on the myosin heads. All right, that was page 10. All right, we will come back to this for page 11 and cover the other half of the picture and the rest of that page. So thank you, as always, for tuning in. The education must go on. And remember, hard work beats talent when talent doesn't work hard. Yeah, I said what I said. Dr. J out.